going well. I hope yours is going well also, Mr. Dara. We're in lecture 19. Apologies for starting a bit late. I had class right before this, and it went over a little bit, so I was a little bit behind, but I think we're rocking and rolling. What we're going to do today is sort of put a cap on equivalent systems in 3 dimensions. And I have 2 examples that I want to do today, but admittedly, what I'm going to be doing is, I don't want to say skipping some steps, but what I don't want to do is just keep repeating the same stuff in class that we've gotten plenty of practice on. And that'll become clear as we get into the examples. But to clarify where we're at, let's just make sure that let's just recap equivalent systems. So, what we did last time in class and what you all did on the homework assignment is really what I would call the pinnacle exercise in chapter 3. And that is to take a system of forces that has a lot going on, and then simplify that into a system with fewer forces, or maybe better yet, a system with one force. And so what I mean by that is, if I have a system that is subjected to a bunch of different loads, oodles of different forces all in whatever direction, I can take that and I can resolve it into 2 forces, right? Or 2 vectors, I should say, a force vector and a moment vector. And so once I have that force vector and that moment vector, I can then ask, well, what if I moved that or put that force vector in a very special place such that that force vector generates the same moment about a point of interest? So the sum of the forces and the sum of the moments are equivalent. And that's probably the pinnacle exercise in chapter 3. After today, in chapter 4, what we'll say is, okay, let's start applying the principles of statics. And so the principles of statics, the principle of static equilibrium, says that for a static system, the sum of those forces and the sum of those moments must be 0. And so chapter 4 is all about determining what are called reaction forces. The idea that if I have a system subjected to a series of loads, what unknown reactions, typically we call them support reactions, are required to keep the system in equilibrium so that the sum of forces and sum of moments equals 0. That's kind of our purpose of chapter 4. But today I want to get into finishing chapter 3. And so what we're going to be doing is looking at equivalences in 3D. Monday we did 2D. And I've got 2 problems. I've got this bracket problem, which got a lot of different forces going all over the place. And then I have this square foundation column. This is probably a bit near and dear for you civils in the room. But either way, there are some benefits to anybody of any discipline. So I have a bracket that is being subjected to 3 forces. And I want to determine an equivalent force couple at point A. Now, what I'm doing for this problem, which I haven't done in the past, is giving you the position vectors and the force vectors. And I'm not doing that to try and make the problem easier. It's just because we've done this before. If I give you a problem and I say, okay, determine the force vector for the force at, let's say, point C. Okay, so let's take the force at point C. Okay, so force at the force at point C. So we're talking about this force right here. I'll draw a little circle around it so we can all kind of see what we're talking about. So that's the force vector we're talking about. You can look at that image and see that it is pointing in the along the XZ plane. So because it's along the XZ plane, you can see that the Y component is 0. I put that as -0J. I probably could have put +0J. It wouldn't matter. And because those are 45-degree angles, I just take 100 newtons or 1,000 newtons, times the sine of that angle, 1,000 newtons times the cosine of that angle, but they're the same, it's 45 degrees, and I get that FC is positive 707I and negative 707J, and that's just because the reason why, negative K. So positive on the I direction, negative in the K direction. It's positive because it's going positive x, but it's going negative in the z. And I'm just using that one as an example. The rest, I'm just doing what I've been doing for position vectors this whole time. The only other thing I guess is worth mentioning is if you look at some of the results here, specifically with the position vectors. If you look at some of these distances, I've got, like 50 millimeters, 100 millimeters, 75 millimeters. But when you look at the position vectors, what is going on with my phone? I'm going to have to turn that off. Oh, I know what's going on. I had an exam in one of my classes, and I'm getting a bunch of pop-ups. My apologies. I have the Blackboard app on my phone, and all these apps or all these exams popped up. Okay. But if you going back to my position vectors, if you look, I have them written instead of as like 100 millimeters or 50 millimeters, I have them written as 0.05 and 0.075. The reason why is because, if you take these, 1,000 Newton forces and multiply them by 75, 100 millimeters, you're going to get some really, really big numbers. And so what I did is I said, let's just calm that down a bit. Let's see if we can turn that into smaller, more manageable values. So I turned the position vectors into meters. So I just took all those distances and divided it by 1,000. So with that, are there any questions, or can we just jump right into this? Because while this example looks really, really complicated, actually what we do in class is going to be pretty short and pretty simple. Any questions before we just jump right in? All right. So let me stop the share, and let me go to share the screen. Hold on. Okay, so here's the problem that we're doing, and like I said, I think you're going to find this is pretty straightforward. And the reason why is because we're still employing two basic fundamental principles in statics. So we're going to be determining that the resultant is the sum of all of my individual force vectors, and then this moment vector, or maybe we'll call it m sub r, like the resultant moment vector, is just the sum of all of my cross products. And so if there's any one lesson I would say about 3D problems is that it could just be kind of time intensive. It just takes a while to do it because there's a lot of grunt work. It's not hard, it's just they can be kind of long. But if anything, this is where your Casio or whatever calculator that you used in the class, if you know how to automate cross products, it'll make your life a lot easier. So first off, let's determine the resultant force vector. Okay. So the resultant force vector, I really don't think, like if you've got the force vectors written out right here, I don't think you really need to do anything fancy with a calculator, because you can just say that you have FB is 300I minus 600J plus 200K, and then put your FC is 707I, and then just go ahead and put the 707K right here, and then the FD is 600I, and this ends up being like 1039J, and there's no K component. You could just add these components directly. It's pretty straightforward. So I've got for the resultant vector, this is easy. So what do I have? 300 plus 600 is 900 plus 707. It ends up being like 1607I. Let's see, I got 1039 and then minus 600, so 439J and then this is going to be like minus 507k. Like that's easy. You know, in order to determine the resultant vector, that's easy. So that's actually part of the answer right there. You know, and again, it follows the same principle that we've been employing. So that's your force equilibrium. So in other words, I can take those three forces and just replace them with a single force vector that equals this. But that's not enough, because I also have to ensure that I'm meeting not just force equivalent systems where the forces are equivalent, but the moments have to be equivalent as well. So I'm going to have a bunch of cross products that I'm going to need to do. So I'm going to have an MB that I'm going to have to figure out. I'm going to have an MC that I'm going to have to figure out. And I'm going to have an MD that I'm going to have to figure out. And ultimately, I'm going to sum those up. Now, how am I going to do that? Well, let's take the first one. Okay, so this is R B from A crossed with force B. You know, just R cross F. Okay, I'm gonna erase these so that I don't crowd this up. Okay, and so what is each of these vectors? Let me scroll up a bit. I'm going to cheat. So this is 0.075 I and 0.050 K. And then I'm going to cross that with my force vector, which is 300 I minus 600 J plus 200 K. Okay. And what that means is, and this is just kind of the thing, it kind of sucks with 3D, but it just sort of is what it is that I'm going to have to do 3 different cross products, okay? Because I'm going to have, I, J, K, I'm going to have 0.075, 0, and 0.05, and then 300, minus 600, and 200. And I'm going to have to evaluate this, and then I'm going to have to evaluate it for the C force and the D force. And admittedly, that it's not hard; it's just a lot of grunt work. But this is where the your Casio can really help you out. So let me pull up my emulator here. So I have here a little Casio emulator. Let me see if I can. Let's see, pop-up display. So I've got that. Pulled up pretty big. Let me see if I can go through this cross product in the Casio. I'll do it pretty quickly. So let's see. If you remember, I actually posted a YouTube video on this. But we'll go through it together. So mode, and then we'll do mode 8 for vector, and then we have vector A and vector B. Actually, I forgot a parenthesis right there. So let's do vector A is the R vector, and then vector B is the force vector. So let's do vector A. Is it going to be a 3-dimensional vector or a 2-dimensional vector? We're going to say it's 3-dimensional, so we do option 1. And then we have our 3 values that we need to enter. So positive 0.075 equals the 0 for the J, so 0 equals, and then for the K, that's 0.05 equals. Okay, and so there's my A vector. And I can clear that. Just press the AC button to clear that, and then I can go to mode 8 vector B, 2, and then it's a 3, size 3. I'm sorry, 1 for 3, and then 300 minus 600, and then 200. And there you go. So I've defined each of those vectors. I can clear that out. And so I've stored that data inside the calculator. I can go to Shift 5 for vector operations. And so this will tell me, so there's dimension, data, vector A, vector B, vector C, and we can do the dot product here. What I want to do is a cross product, so I can just do vector A 3 times shift vector B. And when it's all said and done, you should get something that looks like this. You should get 30i, 0j, and then minus 45k. So I can take this right here. So 30i, 0j, and 45k. So I'll say 30i plus 0j minus 45k. And remember, this is a moment, so it's probably not a bad idea just to keep in mind that that is going to be, this is metric, okay? And so our position vector was in meters, our forces were in newtons, so this is Newton meters, just to make sure that we're clear on the units. So this is meters, this is newtons. Okay. So what we're going to do, I want you to help me out. Okay, so I did the first one. I'm going to have you all do the next couple. So let's do MC. So MC is going to be our R cross F. All right. So, and again, the real point of what we're doing today, I want to make sure that we're comfortable with the cross product aspect of what we're doing. So 0.075i plus j, but this one is minus 0.05k, and then crossed with the force vector, which is 707i plus 0j minus 707k. So I want to see if you all can do this one for me. And just so that everybody's clear, all I'm doing is I'm taking, the force vector and the associated position vector and just doing a cross product. And again, how did I get these vectors? So we're doing all of this from A. So this is my position vector. This is CA. And so you think, well, how do you come up with that? Well, it's a positive in the X, negative in the Z, and so, and same thing with the force vector. So somebody help me out. You can do this by hand, or you can do it in your Casio, however you want to do it. But somebody tell me what the cross product is for these vectors. I'll give everybody a sec on this, but I want to make sure that we're clear on this. Okay. So you got 30J. See, that's what I got. I did get a J component, but I only got 17 points. Like I got 17.68. Check your signs. Make sure that you've got a negative on the K on the R on the position vector. Yeah, that's what I got. I got just zero I minus, or sorry, plus 17.68J plus 0K. And then MD, check your signs. MD, so R cross F. And so the R vector is, what is it? It's 0.1i minus 0.1j, and then it's plus 0k. Maybe I can give me a little more room there. And then it's 600i, and it's 1039j. While you all are working on that one, Mr. Page, did you get the that one figured out for MC? Okay, good deal. Excuse me. Oh, hold on. Okay, 163.9K. Let me see. All right, did anybody else get that? Good deal, awesome. Okay, so got this one and this one. Maybe what I'll do is sort of do what I did before. I had like an MB, an MC, and an MD. And maybe I'll sort of write them out, in order so I can kind of see what's going on. And what do I get? I think I got 30I here. I didn't have a component here. This was 17.68J. And then I had like plus 0J here. This was 0I, 0I, 0J. This was 163.9K. This was 0K. And then minus 45K. I think I got that right. I think I wrote all those correct. Let me know if I missed something. But yeah, that's what we got for MB, MC, and MD, I think. And so the sum of those is, so what do we got? We got 30I, and then 17.68J. And then here, what do we got? We got minus 45 and 163.9. What? My goodness. I'm a popular guy. And so this is, what do we get? We get plus 118.9. Is that, can somebody second me on that? I want to make sure I got the math right on that. Awesome. Okay, so just to summarize what we had 439J minus 507K. And we'll say newtons, and then our moment vector is 30I plus 17.68J plus 118.9K in Newton meters. And so what I can do is I can take that system that has all those different forces on it, and I can say, you know what? Let's take all those forces and just represent it with one force vector and moment vector. Makes it a lot easier to manage. And then what we're going to do on the next problem, the geometry is a bit easier, but we're going to how can I put this? We're going to do a little bit more with the next problem than we do with this one. But before I move on, are there any questions on this? Hopefully you didn't find this to be difficult. It's just kind of like, again, once you get into 3D land, it doesn't really get hard. It just sort of turns into just a bunch of plug and chug, a bunch of grunt work, if you will. Okay, let me go ahead and jump into the next problem. This is our second problem. Let me talk to you a little bit about this problem. And to be clear, this is actually something that you really have to deal with in geotechnical engineering land. I have a square foundation, and that square foundation is being subjected to a series of column loads. So those are the forces from the building that are going to the columns that are applied down to the ground. And so in civil engineering land, the forces that we deal with are very, very large. So it's not that uncommon to just forego pounds and just say we need to express these in kips. In fact, I'm teaching structural analysis right now, which is the civil engineering class after this. And I don't know that we've used pounds at all the entire semester, just because the forces that we deal with are just so large. And so what I want to do with this problem is I kind of want to take it a little bit of a step further. The first thing I want to do is I want to determine an R vector and an M vector, just like I did before. Where we took all of these loads and idealized them as a single force vector and a single moment vector. But then I want to take it one step further, and I want to ask, like, where do I put that resultant vector such that it generates the same moment about the origin? So I want to put that single vector or that single force at a certain point so it generates the same moment about the origin. I'm going to show you how that works. It's pretty slick. Okay, so first thing we probably ought to do is do some numbering. So how do I want to do this? Well, there's no like right or wrong way. So I don't know. Maybe we'll say this is number 1. I don't know. We'll say this is number 2, number 3, number 4. I mean, there's no, I've just come up with something to go off of. Okay. Now, let's take number 1. Help me out with number 1. What is the force vector for number 1? Like if you were to express that 40 kip load as a vector, how would you do that? Somebody help me out in the chat. Negative 40J. And so let's key in on what Mr. Ball said, because that's 100% correct. First off, it's only a J component vector because it's acting downward in the direction of gravity. But then on top of that, it's negative because it's going downward. Now let's extend this a bit. So I'll call it F sub 1 is negative 40J. Now how about number 2? Number 3 and number 4. Think about it like this. Are any of the other force vectors going to be, any different? So if you know how to do F1, how about F2? Like what's F2? Somebody help me out with F2. There you go, right? So this one's going to be negative 12J. This one's going to be negative 8J. This one's going to be negative 20J. So it's going to make our resultant pretty easy. In fact, we could do that probably right now, but I'll hold off and try and make it a bit more systematic. All right, we also need to determine position vectors. Okay, now let's make sure that we're going off of the problem, the problem statement. So give me 1 second. I'll pull up the lecture notes here so I don't have to stop the share and start it back over. So we have determine the magnitude of the resultant along with its location on the map. What we're going to do is, in order to handle this appropriately, we're going to assume that all of the position vectors, let's just measure them all from the origin. So we need to determine an R1, R2, R3, R4 from the origin. Okay. Now I'm actually going to skip number 1. Like let's do one that's a little easier to see. Let's start off with let's start off with R4. Okay. So help me out with this. So we're taking moments about the origin. Okay, so help me out with this. How would you express the vector from the origin to load number 4? Okay, so we got 4i plus 10j. Oh, there you go. There we go. You're right. It's 10k. Exactly right, because we're going along the x-axis and the z-axis. So this is going to be 4i plus 10k. There you go. Exactly right. So now let's go back. Let's do R3. What's R3 going to be? R3 is going to be like that. And so that's going to be 10, would you get 10i and 5k? Yeah, and they're both positive. Okay, now what about R2? Just, there you go, just the 10i. Now, here's the kicker. What about R1? There you go. It's a 0 vector. Now, let's talk about that for a second. Let's try and get some understanding. The R1 vector is 0. So what that means is R1 crossed with F1, what's that going to be? It's going to be 0. It's going to be a 0 vector. Now, before we just start doing crunching numbers, does that make sense? I mean, think about that. We're going to be taking moments about the origin. Okay, so this is where we're going to be taking moments. So take moments here. So if we're taking moments there, we get that R1 crossed with F1 equals 0. But does that make sense? Let's go back to just the basic definition of a moment. How do we define a moment? A moment is defined as a force times a moment arm. Well, force number 1 is going directly through the origin. It would make sense that if it's going directly through the origin, that it would not generate any moment about 0.0. So doesn't it make sense that when we do R1 cross F1, we should get 0? Because if all our position vectors are from O, we shouldn't get any component. Does that make sense? Now the way I want to handle this is I'm going to do it like this. So we've got an R vector, and this is going to be in feet. And so I'm just going to write out each of my my R vectors. And so this was, we had the 0 vector, we had 10I, we had 10I plus 5K, and then we had 4I plus 10K. And then we're going to have our force vectors. And our force vectors, these were going to be in kips. And this is going to be minus 40J, minus 12J, minus 8J, and this is minus 20J. And so before we move on, we can go ahead and say that our resultant vector is the sum of my individual force vectors. And what is that? What is that going to be? So we have 40, 12, 8, and 20. So what? There we go, 80. Negative 80J. So we can simplify that pretty easily. All right, and now we got to do R cross F for each one of these, okay? And this is going to be in feet kips, okay? Now, the first one was easy. The first one was 0. We knew that wasn't going to generate any moment. Now, for these others, you can handle it one of two ways. You could break out your Casio, or you could maybe try and, I don't know, it's like do something on a piece of scratch paper, because, you know, if I take a look at this this first vector here, so I've just got I, J, and K, and it looks like a bunch of zeros, except for the R vector has a positive 10, and then the J vector has, or the F vector has a minus 12 on the J. And so with a lot of zeros, maybe we can, you know, reason this out. Like if we cross out the this, we're not going to get any I component. We're not going to get any J component. But what about the K component? What is that? Minus 120K? Is that what you get? Maybe minus 120K. Because see, it's going to be I, J, K, 10, 0, 0, 0, minus 12, 0. Right? And so if you, you know, cross out the I and the J, you know, you don't get any component there. If you cross out the J, that's going to be zeros. But the K, I'm going to have that minus that, and that's the only thing that actually gives me a number. All right. Somebody help me out with this one right here and that one right there. Let's start off with the third one. So what do you get when you cross 10I and 5K with minus 8J? Sorry, pause. I got something different, because I've got, for this one, I've got an I term and a K term. That's what I'm getting. Yeah, 40I minus 80K. Yeah, that's a negative there. Yeah, that's what I'm getting. What about for this one? I'm going to scooch this over a bit. What about this last one? Anybody got this one for me here? So 200i and minus 80k. That's what I'm getting. Now, if you've got that, let's see. You think you can, I don't know, sum these up? So moment is the sum of Ri crossed with Fi. If you added up all those vectors, what would you get? So like for the I components, I got 240, so I got 240i. And then what are you getting for the k? So there's no j component, but what about for the k? What is that? Is that 80 and 80 is 160, 120? Was that 280? Minus. That's what I'm getting. Somebody check me and make sure I didn't add something up incorrectly. Now, I'm not quite done with this example. I've got something else I want to do, but I don't want to just steamroll through all this. Are there any questions? See, I'm hoping some of the grunt work we could get through kind of quickly because I don't want to, waste our time with that. All right. Now here's the second part of the problem. Okay, I want to show you what's going on with the second part because this is kind of slick. So what I now want to do is I've got my my plate here. So let me draw me a little coordinate system. So here's my plate, which is acting as the top of my foundation. Okay. And so this is the x coordinate system, or the x-axis. This is the z-axis. This is the y-axis. Okay. And what we're saying is that the resultant is 80 kips acting downwards. And so the question becomes, where could I put $80 kips such that it generates the same amount of moment right there at the origin? Well, let's see if we can investigate that. So maybe the first thing we ought to do, let me erase this, put it right here. Maybe the first thing that we ought to do is see if we can figure out what is this position vector. Well, let's check that out a bit. I'm going to go ahead and say that position vector, I'm going to leave it in like variable form. I'm going to say that is some distance times I plus no distance times j plus some distance times k, right? Because I'm going to have to go, some amount this way and some amount that way. But I don't know what they are, okay? And my resultant vector, again, was 0i minus 80j plus 0k. Now, let's do a little bit of algebra. You all are engineering students. You can handle that. Let's cross those. Let's cross those. Let's see what we get. Let's do that. So R crossed with R is I, J, K, Rx, 0, RZ, and then 0 minus 80, 0. And so let's check this out. So I, and then 0, RZ, minus 80, 0, minus J. And so what do we get? Rx, RZ, 0, 0, plus K. And then that's, what do we get? Rx, 0, 0, minus 80. Okay. And by the way, let me know if I got a typo on this. I want y'all to stay interactive. And so we do our 2 by 2 determinants, right? So we do our, products that way, which are positive, and then that way, which are negative. So we get 0 and then minus that, but that's positive because negative times negative is positive. So I'm getting, I don't know about you, but 80 RZ, right? Minus J, and I'm getting 0 there because both of those products are going to give you 0. And then K is minus 80 RX minus 0. So that's I'm getting what? 80 RZ times I plus 0J, and then minus 80 RX times K. Well, let's remember, what are we trying to do here? We're trying to figure out where to put that load to generate the same amount of moment as the system did. What was the moment that we got from the system? The system said that we had 240I plus 0J and then minus 280K. Well, I don't know about you, but if the moment from the resultant has to equal the moment from the system, then that means each of these components has to equal one another. So 80 RZ has got to be 240, and 80 RX has got to be 280. So RZ is 240 over 80, which is 3. And this is a position vector, so that's feet. And Rx is 280 over 80, which is, I think that's like 3.5 feet. So what does that mean? Here's your foundation. And so I can put that load at a certain point right here to where this dimension here, because that was the x-axis, this was the z-axis, that dimension there is 3.5 feet, and that dimension is 3 feet. I don't know about you, but I just think that's really cool how I can take all those forces and just replace all of it with just a single 80 kip load right there. And if I put that single 80 kip load right there, it will generate the same amount of force as all those other loads and the same amount of moment as all of those other loads. I just think that's slick. And so maybe, to formalize it a bit, that's my other answer. I just think that's pretty awesome. How easy that is. How you can take all those forces and just crunch them into that one spot. Are there any questions? I know we're running short on time, but I want to make sure that this is clear. I promise after today, what we talk about, specifically with support reactions, I think there's definitely a bit more reality you can sink your teeth into, because now it's like, okay, great, we've idealized all these forces. What do we do with them? Well, now we got to figure out what's got to keep the structure in equilibrium. So it's pretty critical from here on out. Any other questions? What did finding the R mean conceptually for this part of the example? Which are you talking about, like this part right here or something else? The 80 kips, you're talking about this one. I just want to make sure I'm talking about the right term. You might need to turn your mic on, because I'm having a hard time following I think where you said something about stabilizing. Oh, that's going to be what we talk about after today, are these reaction forces. So the idea behind what we did today is we took a bunch of forces and idealized them as either a single, like as either a force and moment vector, or as just a single force vector at a specific spot. And the idea was just to collapse a bunch of forces all into a single point. Now, on starting Friday, what we're then going to do is say, look, see that plate right there? If I put 80 kips on a plate out in space, that plate's going to start spinning. It's going to start moving. So what are the other unknown forces that keep the structure in equilibrium? That's not something we have to worry about today. That's a Friday and next week task. So we don't have to worry about that just yet. I'm not sure if I answered your question. Yeah, it's going to get pretty slick starting next week. I think you'll enjoy it. I think like the super theory stuff kind of calms down after today. All right, we're running over, and so I'm going to go ahead and call it. You've got a homework assignment that can that'll give you some practice on this, and then we're going to start using this stuff for real. I think starting on Friday. That's all I have, everybody. You all have a wonderful day. I'll see you all on Friday.